Okay. So today we're going to be talking about dynamic programming, so our DP day one. Uh, Oh, okay. So today we're going to be talking about grid paths, the coin change problem, modular arithmetic, tree DP, and also interval DP. So we'll start with a grid paths problem before we talk about what DP is. So we're given an n by m grid, which contains obstacles, and our goal is to count the number of valid paths from our very top left cell to our very bottom right cell. So, and we can only move to the left or down, and also we avoid the obstacles. So we define paths ij to be the total number of valid paths that reach cell ij from our top left corner. So an example here is our base case, which is basically just a case that isn't dependent upon the other ones. And so path 0, 0 would be 1 because the only path from the start to itself is 1. And as we move to the right, we note that there's only one path approaching from the left and none from above. So it's just 1 all around. Similarly, we can go down a column and yeah, only one path approaches from the top and none from the left. And also obstacles are always 0 because no path can reach an obstacle. So paths 1, 1 would be 0. So similarly, we keep going. This one, we can see that it's 2 because we can reach 1 from the top and reach 1 from the left. And we just keep going. And we notice that basically our algorithm is, oh yes, and we're done here. We've reached 4. And we note that basically our algorithm is paths ij is equal to paths I minus 1j plus paths ij minus 1, as long as we can go from the left and the left and above. So yeah, we just sum the paths arriving from the top and left separately. So we can do a live coding of this problem. The same one. It's basically where we have it's a little bit simpler. It's n by n instead of n by m, but the concept is the same. We're given an n by n grid whose square may have traps, and we're not allowed to move to a square with a trap, aka our obstacle. And we want to calculate the number of paths from the upper left square to the lower right square, only moving right or down. So we are given n in our input, and we are also given a grid where a period denotes an empty cell and a star denotes a trap. And also they want us to print the number of paths modulo 10 to the 9 plus 7. And we're going to talk a little bit about modular arithmetic later, but we should be modding after every step to prevent timeout errors. So, okay. So we just set up it really quickly, set it up where we make n the first given number, and we create um a list, wait, sorry. And we create a grid where a grid is basically just what we were given here, put into a list. So I guess our first step is to create a path counter so we know at each point in the path, at each point on the grid, how many paths we can take to arrive there. So we can do a list of lists, and we can just fill it with zeros for now. So since we were given n by n, we can make an n by n matrix or n by n list of lists, I guess, filled with zeros. And we mention our base case first because it's not dependent on anything else. So we can just define the base case, which would be our 0, 0. So only under the assumption that the first block is not an obstacle. So if grid 0, 0 is not equal to an obstacle was a star, then we can do path counter 0, 0 is equal to 1, because there would be one path if the first one is not an obstacle. And now we can start looking at all the other grids in the system, so we can iterate throughout the entirety of path counter and assign the number of paths that we can take to get to each one. So for row in range n, or call in range also n, our first step is making sure it's not an obstacle, because if it is an obstacle, it's automatically a 0. So in order to do that, we just look at our grid. So if grid row call equals star, then we just continue because it's already set as 0 in path counter, so we don't need to do anything else. Now, otherwise, if row is greater than 1, 0, sorry, if row is greater than 0, so that means we're not on the very left. We're not on the very top, sorry. We can do path counter row call plus equals. We can just add on the previous one, so the one on top. Similarly, we can do this with columns, so it's basically the same code. If column is greater than 0, then we can just add on the value of the number of paths from the left. So we can do that. And note that we mentioned we should be modding at the end of each step in order to prevent timeout errors and for it to run too long. So we can just do that by modding path counter. We can mod equals, and we put mod in at the top. So it's just mod equals our mod value. And after it iterates through that, I think we will have our answer if we just print path counter n minus 1 n minus 1, which would be our bottom left corner. Yeah, okay, and we can test our input. And if we run code, we can see that it does give us 3, like the output says. So we can just submit it and see if it's right. Oh, okay, well, I've submitted the same code before and it worked, so we're good. Yeah, and that's how you do this one basically. Okay. So DP at a high level, because we didn't really talk about what DP is until now. So DP is basically a strategy where you break down a problem into smaller subproblems that are identical so that we can compute, store, and reuse answers to reduce repeated computation. So basically, to every DP problem, we have 3 things that we need, which is the state, the transition, and the base case. So the state is the data that you store, so what you choose to define, how you break out the problems. Transition is how you get from one state to the next. And our base case is just the value of a simple state, which does not depend on any other state, which for the one we did, we note that we separated the base case from the other ones. So for the example problem we just did for grid path, our base case is 0, 0, which gives us 1. Our state is the number of valid paths from 0, 0 to ij. So for each ij, so sorry, dpij would be our state, which is the number of valid paths from 0, 0 to ij. And transition is how we get from one to the next. So if our grid of ij is just a dot, we add the left and the right. If it's, I guess if it's a star correction, then it'd just be 0 as an obstacle. So
Okay, so another very classic DP problem is the coin change problem. And the problem is pretty simple. Given an array of coins and target sum, each coin has a negative integer value. How many ways can you sum coin value to reach the target sum? So basically in this example, our target sum would be 3, and we have coins 0, 1, 2, 3. And there are 4 ways to make it. We can choose 1, 2, 3, 0, 2, 1, or just 0, 3. And oops. Okay. So the essential way to do this problem is that for instance, given the coin 1, 1, 2, 3, 4, at each steps, for instance, if we are at the second to the last steps, we decide if we want to use the current coins or not use the current coins. If we decided to use the current coins, that means in order for the previous coins to sum to 7, it only needs 3 because we can spare 4 for this coin. And then if we choose to not use the coin, we want the previous sum to 7 because we're not using this coin, and the previous coins are responsible for the sum to 7. So this is the essential idea for the DP. We consider either we want to take or not take the each coin. And there is a very detailed table that runs through the algorithm. And again, we try to define the state for the DP. In this case, the DP would be the number of ways to form some J using only the first I coins. And defining the base case, DP00 would be 1 because obviously to get the sum of 0 with no coins, there's only one way to make it. And notice that the base case value for DP01, DP02 would all be 0 because if we have no coins, there will be no way to make a sum of 1 or sum of 2. And the key here is the transition. I'm just gonna rewrite it to make sure it's like a straight line. So this again falls to our previous logics, which is that, sorry, this is a plasma. So for the current coins, it only depends on the row before. For instance, for the current coins, if we decided to not use the current coins, that means the previous I coins are responsible for making to a sum of J. However, if we decided to use the current coins, that means the previous I coins are only responsible for making a sum of J minus Ci. If it's a little confused at first, we can look at the table. For instance, yes, for instance, to make, okay, so for instance, for DP 1, basically making a sum of 1 with only the first coin. There are two ways we could get to it. One way is to use it, which we will just use this one coin, and then there will be one way to do it, which follows here. And then there will be another way, which is that we're not using this current coin. However, it's with that we cannot make it, so it would just be 0, and then we add them together will be the total cases. And then something pretty special about this part is that we need to be careful that there will be the case where J is smaller than Ci. So if J is smaller than Ci, we cannot use the current coin Ci because if we use the coin Ci, it already surpassed the target sums. Therefore, we need to like make another two cases in our code. And this follows with the same transition, right? And this is a little special. So for example, if our two previous coins has the value of 1, however, if the coin has value of 2, that means the Ci becomes 2. That means we're adding the rows with J minus 2 instead of just J minus 1. That was cool. And the rest would follow, and then we could reach our final answer 4. Okay. So does anyone has any question over this part? Okay. Anyone has noticed there will be some kind of like optimization over memory? Okay. So basically, as we have like as we talked about, every time we actually only use the rows and the rows before it. So for instance, for all the cases we talked about, we only use the current rows and the rows before it. Therefore, we can, instead of having a 2D DP, we can just make it a 1D DP. And we can make two 1D DP, and we can just have an old DP and a new DP. And we just need to be careful that we need to reset our values each time. So, and we reset old DP to new DP each time, and then the new DP will be covered with the new values in the every loops. And yeah, there is a sideway topic which kind of appears a lot of time in our DP. So we're talking about it now. So basically, you guys probably all know about this. So A mod B is just the remainder when A is divided by B. And the main property that we used for coding problem solving is that A plus B mod C equals to A mod C plus B mod C, and then we mod everything by C. So for instance, 28 plus 23 mod 10, 28 mod 10 would be 8, and 23 mod 10 would be 3, and 11 mod 10 would be 1, which is same as like 51 mod 10. And the same would work for multiplications. So how we use modular arithmetic encoding, it's basically that when we are like computing some very big numbers, such as like the Fibonacci number, which reach to the 10 to the power of 46, it already passes the maximum integer value that Python could take. So the problem would normally ask us to answer it modulo 10 to the power of 9 plus 7. And instead of like taking the mod at the very end with a very big number, which our computer can't do it, we need to mod it at every intermediate steps. And if we look at the grid path example again, we make sure that in each transition, which in each steps in our inner loops, we make sure we mod so that our value never went past to the maximum integer value. Okay.
Our next topic is tree DP. So we talked about trees earlier, so now let's look at a DP problem for it. So we're given a tree with n nodes, and each node is colored either red or green, and our only restriction is that adjacent nodes can't both be red. So the question is, how many ways are there to color a tree? So greens can be near either, but reds can't be near another red. So we notice that node colors depend only on its children colors. So if we have a red node, then it's green children. And if it's a green node, it can be both red or green children. Because green can be next to either, but reds can't be next to reds. So note here that the subtrees are independent of each other because each node is only dependent upon its children and not the children of any other nodes, which means that each subtree is independent. And so our state can be, we can have DPI color to be the number of ways to make subtree I that specific color. So the color would be red or green, and I would be your subtree. So now let's look at the transitions from state to state. So given the subtree, so V, for DPV red, each of its child, which we can denote C, has to be green. And so note that the ways to color each subtree would also be DPC green. So DPC green represents the ways to make this green. And note that as a result, DPV red would be the product of each child and the number of ways to make it green. So if this child has 2 ways and this child has 1 way and this child has 2 ways, then the ways to get V to be red would be the product of these 3, which would be 2 times 1 times 2. And we can see an example kind of here as well. And note that this would not be allowed because red is next to red. So yeah, that's our transitions. And that's our transitions for red. And for green, we note that each child can be either red or green. It doesn't have the same restriction. So then note that for each subtree, the ways to color each subtree would be DPC red plus DPC green. Because it can both be red and green. So the number of ways to get red plus the number of ways to get green is the total number of ways to color it. And so DPV green would once again still be the product of the number of ways each children can be colored. And in this case, each child doesn't only have to be green, so they're added, but then we multiply it together to get DPV green. Does that make sense to everyone? Okay. So our overall solution, note that for our base case, we start at the leaves because there's to color a DPV red would equal DPV green equal 1 because the subtree only has itself in it. So it's just one way to color it for red and one way to color it for green. So each transition, we can see we can apply all previous transitions to get our final answer. The total number of ways to color the tree would just be your DP root red and your DP root green added together. And yeah, based on this, it does need a bit of recursion, as we can see here. So yeah, we start off with green as 1 and red as 1, which would be our base case in this way. In this case, so yeah. So for C and adjacent list, we make sure that the C isn't parent, not the parent node, because we don't want that. And we only consider the children, basically. And we set C green, C red to be DFS CV. And green, we multiply it by C green plus C red, because if you're green, you can have both green and red children. And if it's red, you only multiply it by green. And once again, as noted earlier, we should be taking the mod after each step um, to prevent it from running for too long. And yeah, we return green red at the end. And yeah, note that tree DP is just DFS in disguise.
And our final one would be the interval DP, which probably explained by this example problem. And the problem is pretty simple. There are n slimes in a row, and in one operation, we can merge two adjacent slimes, and the new size would be a plus b, and the cost would also be a plus b. What is the minimum cost to merge the slimes? Um, so when we first look at this problem, our intuition might be to use the greedy approach. For instance, like at every steps, we took the smallest operation. In this case, we have the choice of either one plus four, which would be 5, or 4 plus 4, which would be 8. And if we use the greedy approach, we get 5 and then we get 9 in the end. And the final cost would be 5 plus 9. 5 plus 9, yeah. Because this cost 5 and this would cost 9. However, this approach might not always be the right answer. If we look at a little complicated cases, if we choose like the smallest cost, so compare 9 and 8, if we choose the smallest cost, which would be 8, and then if we at the same like similarly we use the greedy methods, we get a total of 39. However, the optimal ways would actually be 36. So actually the right way to do it is to use DP. And something quite obvious that we can discover is that merging slimes always forms intervals given the rules. So for instance, if we have like slime 9, 7, 7, 8, 2, if we merge these three slimes, it always like represents like a consecutive subarrays, given that the rules of our problems only allows us to merge with like the slimes next to each other. So this is actually very important because this means that each slime could represent a range of slimes, and we could solve this by interval DP. So the DP idea is a little complicated. So suppose we have to make a slime in the range of L and R. We always want to find some M that we must have merged LM and LR. So basically, given the intuition we just talked about, in order to merge a range of L and R, we basically want to find some M that this is already merged and this is already merged. And the state that we would define would be DPLR would be the min cost to make slime L and R. And anyone want to take a guess on the transition of the DP? Like the transition, the hint is that each transition we're like basically like merging two. We're iterating through M and we're merging the two big slimes of with M. Anyone want to take a guess? Try to think about. Okay. So I guess, so basically it's just pretty straightforward. It's just the min cost of L to M these intervals and the min cost of M to R, which is like basically the other intervals. So basically these two slimes represents the interval LM and MR. However, we also need to add the cost of the current step, which would be the sum of L to M and the sum of M to R, which is the sum of L to R. Anyone has question over that? And the base case is also pretty obvious. It's just the base case would be a single slime, which is like the interval from 2 to 3, which would just be a single slime, so it costs nothing. And the order to do this is that longer intervals only depends on the shorter intervals. So when we are coding, we make the loops that make sure that the shorter intervals was merged before the longer intervals. And then when we are searching for n, we make sure the shorter intervals was already pre-computed. Wait, so this is like a single case, single transition example. For instance, this is probably the final step of the example. So we looked over, we checked this to be the first m, and then we check if this is the mean cost, and then we check this to be the m, and then this to be the m, and this to be the m. So in this case, I think the third one would be the mean cost. Okay, and so for the implementations, basically so something very special about this question is that we're using infinity as to initialize just because we're finding the min. And for the base case, as I said, the single slime costs nothing. So we can just initialize the base case. And this part is a little tricky because instead of just directly using L and R, we try to iterate through size. So essentially what this code is doing is that you guys see this clearly? Let's see. Okay. So essentially what the code is doing is that, for example, in the first slide, we're having a size of 2. We pre-computed all the size of 2. The intervals is the size of 2. So we compute all intervals with the size of 2. Then in the second step, when we're computing intervals of 3, we already have all the intervals of 2 and intervals of 1 computed. So we can iterate through n. And for example, if we choose this as the n, this interval of 1 and this interval of 2 are already pre-computed by our first steps. And this kind of like go on. Yes. So we just need to add the current cost of the merge. And I think that's basically what we have for today. Do you guys have any question for this? Okay. So we basically use dynamic programming when we are like trying to break problem into small subproblems. For instance, just to summarize for the grid path, the answer for the one grid could come from the left and could only come from the left and the top. And for the interval DP, we can break a problem into sub-intervals and then do the intervals first. And for the tree DP, the node could also just depends on its child trees, like its subtrees. So that's basically it. Thanks for coming to today's lecture.